Hi guys, so today we will be solving Leetcode problem. Find the longest valid obstacle course at each position. So we're given an array of obstacles and we need to find the longest increasing subsequence ending at each index. So here is a little bit different from the normal longest increasing subsequence in 2 points. So here, so every obstacle is taller than or the same height as the obstacle immediately before it. So it's not strictly, has to be strictly increasing, right? And another point here is that in a longest increasing subsequence, you basically has to just return the longest increasing subsequence of the whole sequence. Okay, so here you need to find the longest increasing subsequence ending at each index, and it has to include the 8 obstacles in the course. Okay, so the approach here basically is the same. In the normal LIS, LIS, you can basically use a DP, which will be O(n) of square in time complexity, but here it will not be efficient enough. As you can see, n can grow to 10 to the power of 5. And O(n) squared would be 10 to the power of 10, right? That's basically surpass the 10 to the power of 9 mark, and it will yield TLE on Leetcode. So there's an approach that uses binary search to find the longest increasing subsequence, and this approach is actually a brain teaser, right? What do I mean by that? It's very hard for a normal person to come up with a solution that use binary search for longest increasing subsequence, unless they spend a ton of time on it. Basically, if I spend a ton of time on it, I would still not be able to come up with that solution, right? So the best we can do is actually to learn the mechanic behind it and how it works, right? So basically here we can say that we will keep track of the longest increasing subsequence of the elements up until an index, right? So bear with me. So for example, if we are giving this example, right? So now I'm coming to 5, I will insert 5, I'm coming to 3. But what will I do here? I cannot append 3 to here, right? Because 3 is actually smaller than 5. But what I can do is that here. Okay, so what does 5 mean here? It means that there is a list, a longest increasing subsequent with length of 1 and n at 5, right? But now we have 3, right? So we have a longest increasing subsequence of length 1 but n at 3. So we will lower this guy, right? We'll lower this guy. So now we come here to 4. I will put 4 here since 4 is larger than 3, and another 4, and I will put 4 here because 4 is larger or equal to 4, and basically 4 here. So now we come to 2, right? We come to 2, and okay, so I check and I see that 2 is actually smaller than 4. So I need to find the index. Okay, so the index where it could fit into this array. Basically it will fit into here, right? If I do 2 here, I will replace 3 with 2, and that basically say that okay, I have a longest increasing subsequence of length 1 ending at 3, but now I have a new record, right? So I will basically replace these guys. So for example, if I have another 3, right? I have another 3, then I can basically do it like this, right? 2, and if I had a 1, I will do it like this. I continuously updating the array to lower the bound of each longest increasing subsequence, right? Okay, so now I come to 1. I will basically do the same. 1, 1, 4. Okay, 4. I add 4 here. 1. Okay, 1 here. And then for each of the iteration, if now the new number is actually larger or equal to the last number in our array, we can simply return the length of the array, right? That could be the longest increasing subsequence ending at ith index. But if that's not the case, and we will do a bisect rect to find the index where we can replace that, and then we will, for example, if I say that I have a 2 here, right? Now the next one will be 2. What will I do? I will do bisect rect, right? I do bisect rect. Okay, now I come here. Okay, I see 4 here, which means that there's a longest increasing subsequence of 2, right, ending at 4. So I will place 4 with 2, and I will just return this index plus 1. That's 2, right? That's basically it. It may sound the algorithm is basically very easy to implement, but it is really hard to come up with, right? I cannot come up with it. The only thing I can come up with is actually here, a naive on of square dp solution, which does not pass. But I'm still proud of myself, since I can recognize that it's a LIS problem, and I can recognize that on of square solution cannot pass, and that leads to the finding of a n.logn solution, right? So now let's implement it. R would be equal to this obstacle path 0, right? And now I need to, what do I need to do? Need to init our result list, and then for n in nums, right, obstacles, if n is actually larger or equal to the last number in obstacles, then we can simply append n into our array, and we just do result append length of n array, right? Else we need to find the position at which we can simply insert this new number into, right? And now what I'll be doing is that I'm going to say result r post is equal to n, and then result append post plus 1, right? And I think I'll just return result. Here. boom. Result should be okay, 1. We should do 1 here because at the first index, then it basically will always be 1, right? Where is ground? Bisect right, or n or post is equal to n append post plus 1. That's basically, why is it wrong? Let me check. So here we return 4 instead of 3. Here we return 3 instead of 1. I'm sorry, it's actually, no, it's correct. Bisect right. I don't know. It seems right to me. Okay, so let's print n r. On 232, okay. That's weird. Oh, sorry. Okay, let's submit it. As you can see, it's pretty efficient. And okay, so let's analyze the time complexity for this. So basically, we do a binary search at each position, right? So it's actually at here, do a binary search. That's log 1, log 2, log 3, and log 4, right? You can say that it's actually O. It's really hard to analyze the time complexity here, but it's simply to say that it's, oh no, okay, because it's not O(n) squared, right? It can be not be O(n) squared because here, 1, 2, 3, 4. I let you guys decide it whether, okay, in the worst case, then it's O(n) squared, in which this worst case cannot happen, right? The time complexity, space complexity is actually O(n). Okay, that's it for today. So I hope you guys understand the solution. It's a really hard concept, right? Basically, a normal person as me cannot come up with it. So don't feel dismotivated. If you can recognize that is the longest increasing subsequence, and you recognize that you cannot use a on square solution, and you must use a n.logn solution, that's good enough. You should be proud of yourself, right? Okay. Try to basically memorize the technique and then understand why it works. It's a crucial part, right? If you do it, if you encounter the same problem, enough amount of time, it will like basically be embedded into your brain, right? Don't worry. Okay, so that's it for today, and I'll see you guys in next video.